The virtual screening approach, first pioneered in the pharmaceutical drug discovery industry, is applied here in the material science field to automate computational analysis and filtering of chemical structural libraries to guide the design of electron acceptor materials for use in organic photovoltaic (OPV) devices. OPV cells hold great promise as viable alternatives to the existing solar technologies dominated by silicon-based devices. Here we see the basic mechanism of photocurrent generation, where light absorption leads to a bound electron-hole pair, or exciton, which can diffuse to the donor-acceptor interface, where it undergoes a charge transfer reaction, forming a hole in the donor layer and an electron in the acceptor layer, followed then by charge conduction. A key challenge limiting the development of OPV devices is the availability of suitable electron acceptor materials. Fullerenes are by far the most common, but have disadvantages. They limit the number of donor materials that can be used to only those that are energetically well matched to fullerenes. They have a small, accessible range of electron affinities, limiting their tuning. They are costly and are highlighted as a key source of instability in lifetime tests of high-performance OPVs. Pentacene, one of the most widely used organic semiconductors, has been identified as a promising alternative that would expand the selection of possible electron donor materials and enable new devices and architectures that could lead to greatly enhanced efficiencies. Indeed, tuning the LUMO energies of pentacene without substantially altering the molecular shape can be achieved by chemical substitution and increase the electron affinity and achieve reorganization energies consistent with efficient electron mobility. Here, we'll examine the use of virtual screening to automatically evaluate the pentacene design space for application as OPV acceptors. Here, the pentacene framework undergoes automatic substitutions of 4 nitrogens, resulting in 135 unique tetraazapentecenes, each of which have their HOMO and LUMO energies, HOMO-LUMO gap energies, and dipole moments automatically calculated, while electron reorganization energies are computed for leading tetraazapentecenes. Here we see an ordered plot of the LUMO energy versus the generated library. Compared with pentacene, all candidates have lower LUMO energies and are all within the range for efficient charge separation. Indeed, the LUMO energies are in a range that is comparable to C60, indicating their suitability as potential candidates for electron acceptors. Coloring the points by dipole moment provides a useful indicator for the charge transport efficiency, as a sizable dipole moment can impede electron transport. Here, the HOMO-LUMO gap energies are shown and compared to C60 are predicted to have lower and therefore more favorable gap energies, which should satisfy a partial requirement for enhanced optical absorption. 15 exemplary tetraazapentecenes are shown here, which have the lowest LUMO energies and low dipole moments, and all of which have computed electron transport reorganization energies less than 0.25 eV and comparable to that of pentacene, suggesting that these structures should show efficient electron mobility when good electron coupling in the condensed phase is achieved. Revisiting the graphs, we highlight another subset of only the relatively inexpensive and more synthetically tractable pyridal tetraazapentecenes, i.e. those with 1 nitrogen per ring, and structures with 0 dipole moments to minimize solid-state trapping defines these exemplary structures. This one in particular has already undergone synthesis and experimental testing. Further synthesis, characterization, and device testing of the electrical properties for this compound and other isomers, guided by the virtual screening results, is underway to establish pyridal tetraazapentecenes as a viable core scaffold for the development of new OPV acceptors.